again, you can. And so the students who weren't able to attend can watch this recording. Okay, so what I have open right now are the lab slides. This is a file that is many pages long because I made videos to go over the calculations to help you with the questions that I anticipate you having. And so I just separated each like new little sentence into a brand new page. And I would like to show you the lab page that I hope you are all looking at. So this is our Canvas lab page for this week. And just to give you an idea, so the procedures, this button right here, those are the entire procedures. So normally you read over procedures, you do a pre-lab, and you come to class and perform the experiment. All of those directions are there. And then this is what you're going to be doing in your group. So you'll watch this video and take the video quiz here. This is a link to just the video. So if you want to re-watch it without having to click through all of the questions, you can. This PDF file. So this is what I'm going to be, the PowerPoint screen that I just had on, I'm going to go back to. I created a PDF file for you to view. And then in your groups, you're going to watch these videos. The first thing you need to do is a review of stoichiometry, of solution stoichiometry. And I posted this from Khan Academy. Khan Academy is a great resource. And I just get a lot of students asking me questions about this because you haven't done solution stoichiometry in quite a while. So take, the 5 minutes, watch this video, take notes, and that will help you with this lab. And then what I did, those PDF directions that you print out here, and I said they're, it's many pages long. So you're going to watch the video and you're going to work through those calculations and then do your own with the data set that I assign you based on either what I emailed you, if you're not here right now, or in this lab class, I'll be assigning you a data set to work in groups. So I like to do this experiment live because I like to let students to work together and talk about the data and talk about the calculations and make it a group effort versus just being, like stuck on your own. Because normally in lab, that's what you do. You work with a partner and you work through those calculations as a group activity. And you'll see, so we have pages 1 to 2, 3 to 6, 7 to 8, 9 to 11. And then also a reminder how to use Excel to make an XY scatter plot. You will be making a graph on pages 3 to 6 on this video. So watch this Excel video. Maybe I'll move it up to remind you. If you don't remember how to make a graph, watch this. And then the post lab you'll be doing on your own, or you can do this together. You can look at the discussion questions together, but the post lab you have to write in your own words. And so that'll be 5 and 6. Questions about the information that is here on Canvas? Excuse me. Okay. So let's go back to these PowerPoint slides. So you should have this PDF open. So you guys can look at this also. Okay, so here, the goal is to determine the equilibrium constant for this reaction. And the key, the product here, this complex ion, is red in color. The reactants are essentially colorless. The product is red. And so what we're going to do, we're going to determine the amount of product in your test tube with a spectrophotometer. And a spectrophotometer is an instrument that can measure the absorbance of a solution. So if the solution appears red, it is scattering red and it is absorbing green. Okay, so that's what we'll be looking at today. So how do we do this? We have 2 different solutions, and I'm going to go over the procedures that you would have been following if you were doing this experiment in lab. I'm also going over the procedures because in your post-lab report, you need to summarize your procedures in complete sentences and paragraph form. So do not copy and paste the procedures. Don't copy and paste and like rearrange the word order. You need to really write it in your own words. So the purpose of the A solutions is because you have a limiting reactant. Therefore, we do not reach equilibrium. Iron is 0.2 molar, KSCN is 0.002 molar. KSC is limiting, so it limits the amount of product we make. So we actually don't have an equilibrium reaction here. All of your limiting reactant is converted to products. So you can calculate that molarity. So in your groups, you're going to watch the video. I'm going to show you how I calculate molarity for A2. I would encourage you to write that down and then do the same thing for the other solutions. You need to give me one example calculation in your post lab for every single calculation you do. The same process you're going to go through for A3 through A7, but write down A3 and that's what you'll include in your post lab. Then for the others, all you're doing is changing the volume of the SCN minus. And so that you can just change on your calculator and quickly calculate this molarity. Table 1, your calculated molarity goes here. The measured absorption, measured absorbance. This is from your student data set that I will assign you. So you will, in your groups, each you have your own notebook you're writing in, write down your measured absorbance. These data tables you can type or you can handwrite. If you type them, you include the typed data table in your post lab report. If you write them by hand, take a photo, include that in your post lab report. Either one is fine. Questions on page 1. So again, the goal of the solution A is because we can calculate the amount of product. Because you know the molarity of the product, you measure the absorbance, and we can create a calibration curve because this will be a linear relationship. So we made the A solutions, you calculate the molarity of the product. So your page 2, that video will show you how to do this calculation. And then page 3, you're going to record the absorbance. So I already said this, but this is what will guide you, the page 3 directions. The absorbance from your student data set, you're going to record in this column. You guys can see my mouse, is that right? That I'm moving?
Yes, we can see your mouse.
Okay, okay. And you're listening, love it. Okay. Step 4, now you're going to make your scatter plot. So we're going to watch that Excel video to remind yourself on how to make a scatter plot. Remember, we did this a bunch with our kinetics graph, our kinetics experiment in graphs. So on the x-axis, you have the molarity of your product. On the y-axis, you have your absorbance, and you see this linear relationship. You're going to fit that data, so just XY scatter plot, fit the data to a trend line, display your equation in the R-squared value. And so what does this do? Because the A solutions, we calculate the molarity because we weren't at equilibrium. We measured the absorbance. We created a scatter plot or a calibration curve. So now I have data points right here at 0, 1, 2, 3, 4, 5. But let's say I have a molarity right here. What would the absorbance be? Well, I would extrapolate up and over and see that. Or what if I had an unknown molarity of a solution, but the absorbance was 0.6? I could say 0.6, go over to the line, down to X, and I could figure out the molarity. That's what we're going to do with the B solutions. So the B solutions, they will be equilibrium mixtures because you have 2 reactants, neither of which are limiting or in excess. So you cannot calculate the molarity of the product because we do not have our numerical value of K. Okay, that's the goal, is to find K. So for the B solutions, you're going to have an equilibrium reaction. You can see the color is red. And with the spectrophotometer, you're going to measure the absorbance. Y equals mx plus B. Y is absorbance, X is concentration. So you can plug in your numerical value for the absorbance of your B solutions and calculate X, which will tell you your molarity of your product. So that's what we'll be doing next. So the B solutions, we follow these procedures. Notice how the total volume in every single solution is 11 milliliters. You know the volume and the molarity of your iron 3+, the volume and molarity of the SCN-, right, our metal center and ligand. So you can calculate the initial molarity of those reactants, right? The initial molarity of the iron isn't just 0.002 because you're diluting what was a 5 ml solution down to 11 mLs total. So we're going to make the B solutions. You're going to measure the absorbance on the spectrophotometer. So you put in a sample, you measure the absorbance, and you record this here. Your student data set will say solution B1 through B5. You write down the absorbance in this column. Then on the next page, step 3, with your absorbance, right, Y equals mx plus B, where Y of absorbance, X is your molarity. plug in the absorbance from your student data, solve for X, and that is your molarity that goes right here. Next, table 3, you're gonna, so that molarity from table 2, the product at equilibrium, that goes in this column. So rewrite that in table 3, and then follow the directions I guided you through it to calculate your initial iron and SCN minus molarity, right? Because we're diluting it down from iron from the 5 mils to the 11 mils total, same with the SCN minus. And then you're gonna use, so get our initial molarity. And then page 8, I walk you through calculating the initial molarity of our reactants. Okay, so I did that on the next page. And then page 9, we're gonna get, you write this equilibrium down. You have your initial molarity, so we're doing step 3. Use an ice box to solve for the equilibrium molarity of your reactants. And why are we doing this? Our goal is to calculate K. And remember, K is products over reactants, but you need equilibrium values. So once we finish table 3, we have our product and our reactant molarities at equilibrium. So then we can go ahead and use those values to solve for K, which are here. So table 4, use your equilibrium values, solve for K. After you do that for each individual B solution, you'll solve an average K, your deviation, and the average deviation. So just the average of your deviation values. A quick question for you guys. So if I have the exact same reaction and the exact same temperature, but all I'm changing are the molarity or the volume of one of my reactants, do I expect the numerical value of K to change or stay the same? What do you guys think?
Change.
So and why do you say change? What do you think? What is capital K? It's an equilibrium what?
Constant.
Constant. Right, it's an equilibrium constant, which is a constant for a given reaction at a given temperature. What does that mean? That means that K value is constant, which means it's not changing for a given reaction as long as your temperature remains the same. So we expect, based on our memory of our equilibrium chapter, for the numerical value of K to be the same for all of these solutions, because it's a constant for a given reaction at a given temperature. Your average K will represent, a pretty good representation of the theoretical value of K. That'll be an experimental value of K. You will see deviations in your K values, okay? They will not be identical, but in theory, they should be. And that's something you'll want to think about for your discussion. So again, the goal is to find K, and I just kind of walked you through the different steps that we're going to follow. So you're going to write all values in table 4 after you do these calculations. These are the discussion points. So in your groups, I want you guys to talk about these, write notes down in your own words. So you should not have the exact same word choice as everyone in your group. If you have questions, page me and I'll come into your group and I will participate in your discussion so that before you leave lab today, you have a good understanding of the answers to these questions, which will be part of your post-lab. And then the last 2 pages are the student data set. So we can see group data set 1, 2, 3, 4, 5, 6, 7, 8. Questions? Okay, so what you're gonna do, I'm gonna send you into breakout groups. Is anyone here who participated in the Monday lab and doesn't need to be in another group?
Me.
Yes, Professor.
2 students. Okay, so what are we? We are, okay, so in your groups, you're going to then go to the spectroscopy experiment page, and I would like you to, if possible, watch that video quiz together. So maybe one person share it and talk about what's going on and discuss the answers as you go through that quiz. And then just continue on watching the videos, writing down notes, using your student data set and asking me for help, and I will join your room and answer and guide your conversations. Okay, I'm gonna stop this recording.